Hello everyone. This lecture will be on error correcting codes. My name is Vinay, I'm a PhD student in the ECC department at IAC. So this lecture will build on some of the previous modules that you have done in the information theory course by Professor Himanshu Tyagi, which is there on NPTEL website. It will build on first of all the uh, lectures on channel capacity, Shannon's channel coding theorem, and also there are some units on the repetition codes, so we'll see that as well. Some prior background that is useful for this particular lecture is some basic linear algebra, something like rank, null space, and other similar things. It's not very much required, but it's good if you know these aspects. All right, let's begin with the lecture. Um, let's review the channel coding setting that you had. In the channel coding setting, you have a source which has certain message M that it needs to send over the channel. This message M is first passed through the encoder. The encoder encodes it to some vector x in 0, 1 to the n. This could be any space x, xn. For simplicity in this lecture, I'll take this to be the binary space 0, 1. Where it passes through a channel. This channel is a discrete memoryless channel. You've already seen what this means. Let's denote this by W. What you get at the output is another vector y in some space yn, which passes through the decoder. Decoder outputs a certain m hat, which is the message that is received at the receiver. Alright. So this is the setting of channel coding that you had. Now the probability of error when a particular message M was sent was defined as a probability that M hat is not equal to M given that M was sent. Right? So we had defined two notions of the probability of error. One is the average probability of error, is given by 1 by M, and then there was the worst case probability error or the maximum probability of error. It is defined as the maximum over all the code words. Of this probability of error when message M was sent. So for the purpose of this lecture, I'll call these x vectors which at the encoder. I'll denote this by C, which refers to a code word, and I'll denote this by small y vector. So these whenever I underline a particular variable, it means that it is a vector, right? All right. In this particular scenario, What does this Shannon channel coding theorem say? It says that for a DMC, all rates below the capacity C of W are achievable. What does this mean? For every rate lesser than C, there exists a sequence of 2 power nr comma n codes with, so here I'll take the average probability of error. You can state the same for the maximum probability of error as well, worst case probability of error as well, 0 as n goes to infinity. Right? You have also seen a quantitative definition for the capacity C of W, which was given to be equal to the maximum over all the input distributions of the mutual information between the input X and the channel conditional probability distribution. Alright. Well, this is all what you have seen before. Okay. Okay, now that we have the channel coding theorem, let's look at it a bit deeper. So first of all, notice that the theorem just gives existence of codes. It only says there exists a sequence of 2 power nr comma n codes. It does not say anything about how to construct these codes. Okay. Moreover, the statement of the channel coding theorem is an asymptotic statement. That is, it has something of the nature of as n goes to infinity. The block length that you are working with goes to infinity. Well, this is not of much use when you are looking at a practical scenario where you have to operate with on finite block length. So in practice, only finite block length, and so what can you say in such a scenario? Moreover, in practice, you also need the encoding decoding mechanisms to be simple. Well, if you recollect the proof of this channel coding theorem, the achievability uses a random coding argument. Such random arguments are hard to implement in practice. Hence, you need encoding and decoding mechanisms which are simple, which can be implemented. Okay. More so, these encoding and decoding operations, uh, so you would have, in practice, you would have somewhat more information while designing a communication system. You would know for what kind of a channel you are designing or what kind of errors the channel introduces. So in practice, while designing these encoding and decoding operations, these have to be taken into account. Okay. So the bottom line is that we have to propose encoding and decoding operations so that these errors that occur in the channel can be corrected or detected. Now the approach that we take in this particular field of error correcting codes is that we take an adversarial approach. That is, we assume the errors that can occur in the channel and try to design code words and see how these perform in terms of the rate and the probability of error. All right. So for the purpose of this lecture, I'll assume that we are working with the binary symmetric channel with crossover probability delta. So what this means is that let me draw the figure first. Yeah. So what this means is that the 0 turns into a 1 and a 1 turns into a 0 with probability delta, and they're received as is with probability 1 minus delta. All right. We have also computed the capacity of such a channel, which is given to be 1 minus h of delta, where h is the binary entropy function given by this expression here. Okay. And if you look at a plot of this, it looks something like this. Because the h of delta is a concave function. So make it half. Okay. So with this background, let's see what should be done. So the basic aim in error correcting codes is to come up with these code words, come up with these mappings, encoder and decoder mappings, so that the errors that occur in the channel can be corrected, and this can be done in an efficient manner. Okay. So let's first look at the encoder. What should the encoder be? So the encoder is always firstly it is a 1-1 mapping. 1-1 mapping from what to what? The 1-1 mapping from the set of messages to the channel input. Okay. So for example, if you, let's suppose this is your space 0, 1 to the n. All right. Now Now there are some of these which get mapped to the messages 1, 2, 3 till m. Alright. So why should this be a 1-to-1 mapping? Well, that is because once you decoded the receiver, so the received word y should be able to decode it to a single message vector. Now if you map multiple messages to the same c or x vector here, then when you decode and obtain a particular c hat, let's say you obtain a c hat at the decoder, once you obtain a c hat, if the encoder mapping is not 1-1, then this could result in multiple messages m1 and m2. So you won't know which of these messages was actually sent. Alright, and hence the encoder mapping needs to be a 1-1 function. Let me write that down here. Alright. So essentially, the encoder, it maps each of the m messages from 1 to m to a subset of the space 0, 1 to the n. This subset is usually referred to as the code book. Okay. Let's look at some examples. Firstly, let's take the case of a repetition code, which you have already seen. So if you take a R-fold repetition code, so let's take suppose R is equal to 7. So if you get a 0, it gets encoded into this. If you get a 1, it gets encoded into this. Alright. So firstly, what is the rate of the code? Rate of the code is the, so you are sending one message bit for every 7 bits. Right, so the rate is 1 by r, or y is equal to 1 by 7 here. Alright. So the encoder, if you look at the code book in such a scenario, what you have is you have this all the vectors in 0, 1 to the 7, but all you're using is only two of these vectors corresponding to this all zeros vector and the all ones vector. Okay. Now if you use a majority decoder, the receiver, that is if the received code word y has greater than r minus 1 by 2 ones, then you declare it as a 1. Then you declare the message sent to be a 1. If uh, if it has greater than r minus 1 by 2 zeros, then declare the message bit sent to be a 0. So this is the optimal receiver for this particular, optimal decoder for this particular code. Hence, the repetition code can correct up to r minus 1 over 2 errors. For example, if your received vector y is this vector, the decoder, since it's a majority decoder, it will see the number of zeros. Since the number of zeros is greater than the number of ones, it will output the all zeros vector, and thus m hat would be 0. Alright. So in this particular this particular scenario, r minus 1 by 2 is 3 errors. It can correct up to 3 errors. Here there are just 2 bits which are in error, and hence these can be corrected. So that was the repetition code. Let's look at another code to better understand this. This is a len 7 single parity check code. So here your code word is the initial, is the message, say m1 m2 okay, sorry, length 8 m7 along with a parity bit p. How is this p determined? So the parity bit is the sum of all message bits. So m1 to m7 are the message bits. Okay. Uh, so an additional parity bit, which is found in this particular way, is appended along with the message bits and sent over the channel. What this ensures is that there are even number of ones in the code word. In C. Okay. So what is the rate of this particular code? Now for every 7 message bits, we are sending 8 coded bits. Hence the rate is 7 by 8. Okay. Going back to our code book. So what you have is totally 0 comma 1 to the 8 is totally 2 power 8. Out of the 2 power 8 vectors, you are using 2 power 7 as code words. Okay, because once you fix the first 7 bits, the last bit is fixed. The parity bit is fixed. Let's see an example of this as well. We have 0, 1, 1, 0, 1, 1, 1. So if this is the message bit that is sent, the appended bit would be a 1, since there are odd number of ones here. So in order to make the total number of ones in the code word even, you would have to append a 1. Decoder that can be used in this scenario. So decoder outputs the received code word itself. Y has even parity. By even parity, I mean that the number of ones in the received code word is even. Otherwise, it will output an error. Okay. So now, notice that this code can only detect a single bit error. So if there is a single error in any one of these positions, the parity, that is one of these bits is flipped. That is one of these bits is flipped. Then the parity equation is not satisfied, and hence you can detect whether there is an error or not. However, you cannot correct the error. So from these two examples, you can see a particular. You can see that there is a trade-off. What is the trade-off? So in the repetition code, you use just 2 code words out of totally 2 power 7 vectors that are present in the channel input space. Whereas here you used half of the vectors present in the channel input space. That is, you used 2 power 7 as code words out of 2 power 8. Okay. However, the repetition code was able to correct up to r minus 1 over 2 errors, whereas the length 8 single parity check code, it could only detect a single bit error. It could not correct any error, any of the errors. Hence, there is a trade-off. What is the trade-off? Trade-off is to transmit as many messages as possible, which is the same as saying high rate. You want high rate. At the same time, you also want error correction capability. Alright. Okay, so there's a trade-off between these two. So for high rate, you should choose a large number of points within this space. You choose a large number of points within the space, but for error correction, so when you choose a particular code word within the space, when it passes through the channel, it can get transformed into another code word, yeah, another vector in the space. Now, in order to have good error correction capabilities, if this transformed received code word, the y is sufficiently far from other code words, then you can correct the error by using a suitable decoding algorithm. However, if you have too many code words in the space, as in the length 8 single parity check code, there might be multiple code words within this within the neighborhood of the received word, and hence error correction is difficult in this particular scenario. This is the trade-off that I'm referring to here. Okay. Okay, so the objective now is to transmit as many messages as possible, but with good error correction capability. So one of the first breakthroughs in handling this was by Richard Hamming in 1948 via the Hamming codes, which are now known as the Hamming codes. So for this, to explain this, okay, let me read that. Okay, so let me explain this with the 7-bit Hamming code. So you have 4 message bits. Say U1, U2, U3, U4, and these 4 message bits are encoded into a code word of length 7 with 3 parity check bits. Now, how are these parity check bits formed? For this, it is good to explain this using the following diagram. Sorry. Okay. Okay. So what this diagram is saying is that, so for the first parity check condition, so how is P1 obtained? P1 is obtained by taking the parity check of this particular, parity check of this particular circle. So that is what I have written here. Similarly, other 2 parity check equations are also written appropriately. Okay. So all the operations here are mod 2. Okay. So this was the code proposed by Hamming. So firstly, what is the rate of this code? The rate of this code is you're encoding 4 message bits into 7 code bits. So the rate is 4 by 7. Okay, so this is k by n. Okay, so once you, let's suppose at the receiver you receive y given by y1 given by this vector of 7 bits. Now, if suppose a single error has occurred in the channel, then this can be corrected easily. Why is that so? Suppose the error occurred in the one of the bits P1, P2 or P3, then only one of the parity check equations corresponding to that parity is affected. If the bits U1, U2 or U3 are affected, then two of the three parity check equations are affected. That is, they are not satisfied. By saying it is affected, I mean that the parity check equation are not satisfied. Similarly, if the bit U4 gets flipped in the channel, then all the three parity check equations are not satisfied. So when this vector y is received at the receiver, if a single error has occurred, by noting which of the parity check equations are not satisfied, the location of error can be found. Okay. So this code is single error correcting code. It can also be verified that it's a double error detecting code. So if there are two errors in the channel, suppose suppose U1 and P2 are the bits that get flipped in the channel, then while the parity check equation corresponding to P2 is still satisfied, the parity check equation corresponding to P3 won't be satisfied because U1 is in error. Okay. So you can detect that there is uh, there is an error, but you won't be able to correct it. That will, since you won't know that it is a double error, right? So this is the Hamming code that was proposed by Hamming. Um, so more generally, this can be written in the following form. So what are the code words in but this particular scenario? Hmm? You can define the following matrix, the parity check matrix. All right. This times, maybe I'll erase this. This times Q1, Q2, Q3, Q4, P1, P2, P3. So all the three parity check equations which have been written here can be written and expressed in this form. It should be equal to 0. Okay. So I'll skip the mod 2 from now. It is understood that all the operations are being done on the binary vectors. Okay. So for example, here the first multiplying the first row and this vector here gives u2 gives the first parity check equation p1 plus u2 plus u3 plus u4 is 0. All right. So this matrix that I have written here It's usually denoted by H and it's called the parity check matrix. What this is saying is all the code words, if you denote the code words by C, then H times C transpose is equal to 0. Alright? Okay. So more generally, what are the code words? What is the code book? C is the set of all vectors such that H times C transpose is equal to 0. In other words, it's the null space of H. Okay. So this is a starting point of what are called as linear block codes, which form a very important class of codes in which are used for error correction. So most of the advanced codes are built upon this particular structure. So they have a very similar structure. We'll come to some of the ones which are used in practice. But for now, yeah, all of them have a similar structure but with different parity check matrices. So these are the null spaces of a parity check matrix H, which is of in this case it's a matrix of dimension n minus k cross n. Okay. Uh, so these form the basis for more advanced codes. But so why is it called linear, by the way? It's called linear because if C1 and C2 belongs to this code, then C1 plus C2 also belongs to this code. That is easy to see because H times C1 plus C2 whole transpose is H times C1 transpose plus H times C2 transpose, both of which are 0 because C1 and C2 belong to the code book, right? So in our earlier codebook space, so you have 2 power k code words out of 2 power n total number of vectors, right? So the parameters that define a linear block code are first of all the block length, here n, the dimension of the code, which is given by n minus the rank of h, denoted by k, right? And lastly, okay, so recall our examples of the repetition code and the single parity check code. So one aspect was to determine the number of vectors, the other was to characterize the error correction capability of the code. Okay, this is done using what is called as the minimum distance. How is this defined? Dmin for a linear code is defined to be the minimum Hamming distance between C and C prime. But what is the Hamming distance? This is the Hamming distance which is defined as the number of bits to flip in C to obtain C prime, right? Okay. So if you define the Hamming weight to be the Hamming weight WH of a code word C is the number of ones in C then the Hamming distance between C and C prime is the Hamming weight of C plus C prime, because that on a binary field minus and plus are the same, and hence this can be written like in the following form. What this also means is that the minimum distance code can be written as the Hamming weight of C plus C prime. Now, since C is not equal to C prime, then C plus C prime can not be 0. Also, since it is a linear code, C plus C prime is some other code word within C, within the code book C. Hence, this can be written as the minimum weight of some code word C, where C is not equal to 0, the 0 vector of the Hamming weight. Alright. So the way to find, one way to find the minimum distance is to list all the code words in your code book, and then look at the vector which has the least number of ones in it. The least number of ones will give you the minimum distance of the code. So one thing to clarify is that in the definition of the code book, this is the 0 vector, right? Transpose equal to 0, it's a 0 vector. Okay, so now, so these are the three parameters that underline the any linear code: the block length, dimension, and the minimum distance. So usually the linear codes are referred to as NKD linear codes, which means that it has a block length n, dimension k, and a minimum distance d. So the minimum distance, I mean, if you recall this figure, uh, so when a particular code word is transmitted over the channel, it gets morphed into a different vector within the space. So the minimum distance tries to capture what is the maximum distance between the received vector and the code word that was sent, which can be corrected. Hence, if you have a NKD linear code, the code can correct up to d minus 1 over 2 errors. Right? This is something to keep in mind. So I won't give a proof of this, but the way to show this is that you can always find a decoder which can correct up to d minus 1 over 2 errors. So you can construct a decoder in a particular way. Right? Okay, so now that we know the structure of a linear code, how are the encoding and decoding operations done? So recall that our motivation is to come up with simple encoding and decoding schemes. These should be better than a random coding scheme or something like that. So first of all, let's look at encoding. So for this, we'll take the messages to be, so I already mentioned that first of all, the encoder is a one-to-one mapping. So, but so you have this huge space 0, 1 to the n, out of which you need to choose some 2 par k vectors. So we had 1, 2 till m messages. So for convenience, I'll take this total number of messages to be 2 par k. So you have 1, 2 par k messages, and these should be mapped to some 2 par k vectors chosen within this codebook C, right? So it should be a one-to-one mapping, so, but you can't map any vector to any of the vector. It should be mapped carefully. So that carefully is such that you respect the minimum distance property of the linear code. So how do we do it? So for this, we'll use what is called as a generator matrix. What is a generator matrix? So it is a k cross n matrix which is formed by using some basis vectors from C. Okay. So you take a basis of C this of the code space, and then stack the particular basis vectors in the form of a matrix to obtain the generator matrix. Now if you have the generator matrix at hand, then you can obtain the code word C by simply pre-multiplying M with the generator matrix. Okay. Now there are okay. So, but how do we obtain this generator matrix? So one particular one way to obtain this generator matrix is if your linear code is specified using a parity check matrix of this form. Okay. So if your parity check matrix is in this particular form, you can find the generator matrix in a simple way. even if the parity check matrix is not in this form, it can be brought into this form using some row operations in order to obtain the in order to use this particular result. All right. So essentially, what I'm trying to say is that these GIs, see, these GIs are nothing but elements of C. So they satisfy H into GI transpose is equal to 0. Now the generator matrix, so what needs to be checked in order for this proposition to work is that H into G transpose is equal to 0. Alright, which you can check is true. Okay, so the generator matrix is basically obtained by stacking code words which are linearly independent, so k code words which are linearly independent in the form of a matrix. So let's do an example. We already saw that the H matrix for the Hamming code was given by this. Alright. So notice here that this H matrix is in the form A and I n minus k cross n minus k 3 by 3 and A 4 by 3. Sorry, 3 by 4. So the G matrix can be obtained as okay. So this is generator matrix for my code. All right. So now, for example, if you have a particular message M to be 1010, you can actually find the code word by doing M times G, and I think you'll get something like 1. Okay, so this can be checked. Also, another exercise for you is to check that the minimum distance of this code is 3. I've already mentioned how this can be done. So one way of doing this is to list all the 16 2 power since the dimension is 4, 2 power 4, 16 code words out of the 2 power 7 is equal to 128 vectors, and see which has the minimum distance, minimum weight. Okay. Okay, so that was regarding the encoding. So you see that it is a very simple process in the sense that it involves once you know the generator matrix, it just involves multiplication of this of the message vector with the generator matrix. So what about the decoder? For the decoder, so when the code word is sent across the channel, you receive a particular vector y. All right. So the input to the channel is also a 7 bit vector, and the output of the channel is also a 7 bit vector. So for example, if you transmit this first Okay. So the channel in this particular scenario can be seen as adding some kind of a noise, and this additive noise is simply a binary vector. So in this particular scenario, when you have these two, this to be the code word that was sent and this to be the received vector, the error vector that gets added by the channel is this vector. Okay. Okay, so now that now you so you are the receiver, you are sitting at the receiver and you have received a particular y. How do you decode to obtain the code word that was sent? That is the question. So for this, we evaluate something called the syndrome, which is nothing but h times y transpose. Okay, so you know y and you can compute this. You already know the code and you can compute this particular syndrome. So what is it in terms of C and E? This is S times C transpose plus E transpose. Now since C is a code word, H times C transpose is 0, and hence this is nothing but H times E transpose. Alright. Now we already mentioned that for the Hamming code, the error patterns, the Hamming code can correct all codes with single error, right? So the error patterns that can be corrected are of this form. Similarly, till okay. Okay, so since the Hamming code corrects only single error patterns, these are the error patterns that can be corrected. Now, what do each of these error patterns result as the syndrome? So, what is this particular quantity? So, if it is all zeros, it is 0. Now, each of these error patterns, when you multiply it with h, it just selects that particular column of h. So your h is here, it selects the particular column. Okay. So for this case, 0 1 1 0 1. Similarly, this will be 0 0 1. Okay. Okay. So once you receive a particular vector y, you can compute the syndrome. So let's do an example for this to understand this better. Suppose your y is 1 0 1 0 0 1 1. The syndrome that you obtain is 3110. All right. So what this means is that so from this table that we have here now, what this means is that the error pattern that got added is this particular vector. This in turn says that the error occurred in the third bit, which is this particular bit here. So the actual code word that was sent was this. Hence you can correct a single bit error using this particular decoder. Notice here again that the decoding algorithm is very simple. It just involves finding the syndrome, and if you which can actually be pre-computed and stored at the receiver for different error patterns that occur in the channel. Hence, we have easy encoding and decoding operations using linear codes. For linear codes. Okay, so how does all this relate back to what you learned in the information theory course? So we have described a class of codes called as linear codes, but first of all, so some of the questions that you should ask is, do these codes come anywhere near to achieving the Shannon capacity? Um, So one way is that similar random coding argument can be used in this particular scenario as well. You have the generator matrix and you choose entries of the generator matrix to be either 0 or 1 with equal probability. So in this particular scenario, it can be shown that that these linear codes with that particular generator matrix can actually achieve the capacity of the binary symmetric channel. However, well, this is not using the power of the linear codes that we have developed. So we would want more deterministic codes and not random code constructions like this. So what about deterministic codes in the sense not codes which just show some kind of an existence of a particular linear code? We want to have some explicit constructions of the code. So in this scenario, there have been many codes proposed, similar, called as low density parity check codes. Polar codes and turbo codes, which are known to be capacity achieving, approaching at least. So let me just give a hint of what LDPC code. I can't go into the details of all this. So that will be done in a full-fledged course on correcting codes. But I'll try to give a brief idea of what LDPC codes are. These are known to achieve the capacity, Shannon capacity. So you already saw that we in the linear code we had this parity check matrix. Now the parity check matrix is a n minus k cross n matrix. The rank is n minus k. It can be a. I mean, you can always add two parity check equations to get a third parity check equation and append it to the parity check matrix. It doesn't alter anything. So nevertheless, it is n minus k. Let's take it to be an n minus k cross n matrix. Or in general, it has around theta of n square entries. Okay. Uh, so if you take around half of them to be ones, there are theta of n square ones in H. Alright. In LDPC codes, the number of ones is of the order n instead of n square. Alright. So this is the first difference between normal linear codes and LDPC codes. Moreover, each row has the same number of ones and each column also has the same number of ones. Okay, in an LDPC code. So the analysis of these codes are difficult, but however, these form a straightforward extension of whatever linear codes that we studied in this particular lecture. All right. So the encoding is done similarly, whereas the decoding uh, use more sophisticated algorithms called as message passing or belief propagation algorithms. At the decoder. All right. So okay, that concludes this lecture. So in summary, what we did, so we first motivated for explicit code construction from the Shannon's channel coding theorem. We saw parity check and Hamming codes. Then we developed some theory for linear codes. We saw how the encoding and decoding is done. And finally, some background on capacity achieving codes for scale. Right. So that concludes this lecture on error correcting codes. Thank you.